This is the lecture number 6 of the artificial intelligence course. In this session, we are going to see the techniques which are beyond the classical search. So what I was telling that actually, whenever you want to solve a particular problem, your approach is generally incremental. So you keep increasing your domain, and after that, if this is what the problem is, sometime you would be able to cover all the things, and your problem would be solved. So there is a standard method, means they define a kind of way in which the things are going to proceed. Here also things are defined, but actually what happens that that search may go from here. Search from in this particular scenario also I can say something like this. Search goes from here to here, and then again comes here. Then again it can go here, and again come here. So anything could be possible. Anything. So means when you are going to be better and worse, all these things comes very unique way. Let us try to see once again. So we would start from the things where we left in the last class. The first thing that was the hill climbing. Basic idea is very simple. That if you are somewhere, for example, let's assume that x and y are two variable, and you want to find out that where is the maximum value. So let's assume without loss of generality that there is some point which has the maximum value. So my objective would be find out this particular value, the place where this particular maximum value is. So how can I reach it if I am here? So if I am here, so what I should do if I am here? So I would see all the values into the nearby things. So definitely I want to optimize some objective score. So I would see that what is the score into the nearby. So if let's assume that here the score is 10 and here the score is 5 and here is 20, here is 15, here is 9, here is 19, here is 22, here is 11. So definitely you are going to select this particular direction. From here you are going to into this particular direction because the value is higher. So you see nearby places and then find out which is the largest value. So the algorithm is very simple. It says that you find out the in your list of after the problem formulation, what you see that what is the highest value successor into the current, means who is the successor, means these are the places where you can go. Okay, so who is the having the highest value? So you are going to call it as a neighbor. Okay, so if all these values which are there, if you consider and you find out there this has the highest value, and if this highest value is lesser than your original value, then means what? No, no, you are at the peak. If the highest value into this particular neighborhood is say 10, 9, then would you like to proceed because here the value is 10? So if the highest value is less than the whatever your current value, if you see that what is my current value is 10. If the neighborhood value is lesser than this, then you need not to do anything. Just return the current state because you are on the already on the maximum. Otherwise, you go to this particular place. So by this you go to this place, then after that you nearby find out some other place, and after that you will be able to reach in this particular place. However, you know that we have discussed into the earlier into full detail that it may be possible that there could be small pockets where it is a maybe local maxima. So you can be going from here to here and then you would be stuck because now you would not make any kind of progress. We have seen an example also in the last class that that let's assume that I'm going to solve a problem of problem of 8 queen problem, and here the issue is this, that you have a chessboard and you have to put the 8 queens over here such that none of them are attacking to each other. You know that you cannot put two queens into the same row. It means what? That you can put the queen into this particular row in this particular column anywhere. Similarly, in this particular column anywhere. So how many ways you can put? 8 ways, 8 places, na? Because if say 8 cross 8 thing, so 8 places would be there where you can put it like that. Here also you can, there are 8 places, here also 8 places. So total number of places is 8 to the power 8. So this is the space in which actually you want to find out the solution. Definitely this is a upper bound and there would be some because you know that you always can rotate this and find out the similar kind of thing. So definitely it is lesser than this, but broad idea that 8 to the power 8 things are possible. Okay, so if you want to find out the successor, for example, if there is any board position, let's assume that you are into some board position configuration. You are here in some configuration. Okay, So and in this configuration, if you want to go to the next configuration, so what you can do, so whatever, for example, if there is a queen, you can advance it in, put it somewhere else. Okay, yes or no? That if you there is a board position and this is not a solution and you want to change the to any other nearby states, so what you can do, you can forward this particular queen, any queen you can forward. So if you forward this, how many places are there to be forwarded? 7 places, na? Because on one place it is there and 7 places you can forward a particular queen. How many queens are there? 8. So branching factor is this much. So this much, this is the branching factor. These many things you can advance in next as a next move. So 56 successors are there. Any questions on that? Okay, and when you advance it, you actually end up into this kind of scenario. For example, if this is the board position, if you take it here, and let me say that there is an heuristic function that defines the goodness of my property, and the heuristic function is this, that number of pairs of queens that are attacking to each other. Okay, so this is the board position. So how many pairs are attacking here? One pair. Okay, because these two are attacking. Is this also attacking? No, only these two are attacking. So if I put one more, for example, here queen. Okay, in this how many are attacking? Okay. So you can see that this one pair is also there and one pair. So now 3 pairs are attacking. So I'm going to create a, let's assume that we have a heuristic cast function that tells that what is the number of pairs which are actually attacking. Okay. So this actually is an example board position where let's assume that you are, if you, so again, so so if you, for example, if you advance it here, so 14 pairs would be attacking. If you put it here, again 14 would be attacking. If you put it here, 16 would be attacking. If you put this thing here, then 14 would be attacking. Put it here, 12 would be attacking. 12 pair would be attacking. So ultimately, when your answer comes, this value should be 0. Okay, no one is attacking. You should reach to this particular position. So these values everybody understand. So here let's assume that here these are the position of my queens, and if you shift it here, then for 15 would be going to attack. If this you shift it here, then 15 would be going to attack. So ultimately, finding out a good move is going to reflect it in this way, that find out what is the minimum value into this particular one. Okay, in this particular table. So I think that 12 is the minimum value possible. So your next move should be either you put it here or you put it here. Okay. So this is the kind of board position. So what I want, that I have defined a heuristic function. I want this value to be 0. Okay, to get the answer. Any questions? Any problem on that? No. So this, for example, if you see this one, so here if you see, so you can see that how many pairs are attacking here. So here many pairs are attacking right now. Well, right now actually 17 pairs are attacking. But if you see here, so you can see that this is a different kind of board position where only one pair is attacking. Okay, one pair is attacking. So this is a better position. So how come you can come from here to here? So maybe you shift it here, then you become 14, then you shift it here, then you become 12, then you shift is here, some everything you can shift, and then you can reach to this particular board position. How to reach this is again a important problem. Okay. By your experience, you know that it may be possible that since all these things are possible, that all these things are possible, means with respect to a value of x, if you want to find out how good this solution is, okay, so it is something like that. So your objective is generally find out the value of x that is with respect to this particular point, with respect to this particular point, because this is the best point. Okay, because this is the best point. But if you start here, for example, if you start here, you see here, you would be able to reach this place only. So is it, I'm sorry, I think if you start here, let me say like this, if you start here, then you would be seeing and you would be reaching to this particular place only. So going to ultimate maximum may not be every time possible. Okay, because it also depends upon the where you are actually starting. So you you can say that sometime it may be you may reach to a position where no further progress is could be possible. Are you able to see that? If you are here, then no further progress is possible because I'm sorry. I think if you are here, no further progress is possible. If you are here, no further progress is possible. If you are here, no further progress is possible. Okay. Even if it is not a solution, let's assume that this represents the maximum value. Okay. And this happens because of what? Local maxima. Here is the local maxima. Ridges. So this is a ridge actually. This area is a ridge. Okay. What happens that all the values are actually same. So if all the value not the same actually what I wanted to say that let's assume that it is something like this. Okay, if it is something like this, this and ridge means what that values have very small variation. Okay, they have variation, but this variation is very small. So if you go look closer, you can find out many many maximas over here. So you would be stuck at this particular place. Okay. Next region could be plateau. So you can see that all the values are same. So if you are here, you see that sometimes it may be possible that you reach to that particular board position that if you move any one of them, it is not going to give you any kind of advantages. So let us see some statistics starting from the randomly generated 8 queue states means you 8 queens you are going to randomly in every column you are going to put one queen. And after that, you wanted to solve this particular problem. So if you randomly generate the 8 queuing state and apply a hill climbing in the same way that we have talked about here, that you randomly generated and see the computed all these values, and then you are going to advance in some way so that you can be moving in some direction. So what happens that 86% of time it gets stuck. Means you reach to that particular place that every value is same. Now you cannot make a progress. 86% of the time means 14% of the time you are going to get the solution. And if there is a solution and you succeed, only 4 steps are needed. So it's very effective. In the 4 steps, you can get the solution. And 3 steps when it is stuck. The state space, you can see that it's very large, but you randomly generate some queen position and try to see that what is nearby, and based on this you do some kind of move. After 3 moves you would be stuck, you would not be able to move anywhere, all the values become same. If you succeed, then within 4 steps you would be able to find out the answer. Okay, this method everybody understand that you randomly generate the position, you randomly generate the board position, and then compute that in which direction you have to go. In 4 steps, you would be able to reach. But the probability of reaching this is very less. What is the probability? Is 0.14. Everybody understand this? If I say that 86% time it is stuck means 0.14. And if you understand this particular part, I think I can tell that if the probability, for example, if I say that the probability of winning a ticket, let's assume that you are playing you are purchasing a ticket of a lottery ticket, and let's probability of your winning is 0.2. So let's assume that probability of winning on a ticket is 0.2. So if you take 5 tickets, so what is expected? So if you take 10 tickets, how many tickets are going to be win? What is expected number of tickets that are going to win? 2. Yes or no? If the probability of winning is 0.2, you purchase 10 such tickets, then how many tickets would be successful? 2. Yes or no? Can you tell yes or no? Anybody? So you know that if you have a coin, the probability of getting hit is how much? Half. Okay. So if you flip it 2 times, then the probability expected number of hit is going to be 1. Yes or no? If you don't understand this, try to understand that flipping a coin probability of getting hit is half, heading is half. If you flip 100 number of time, what is expected number of heads? Batao bhai, what is the problem? Nobody is typing.
50.
50. So it is going to be 50. Okay, so how come you got the 50? You multiplied the number of things with this and you got the 50. Okay. Yeah. So I think on the chat you may be typing it. Yeah, I think people were typing. Okay. So so what my question is that if let's assume that in some setting the probability of getting winning a ticket is 0.2. So if you purchase 10 tickets, how many if you are expecting that they are going to win? 2. Okay. If you want to get one success, then how many tickets need to be purchased is 5. Okay. Brahmanand, once again, let's assume that there is some game where the probability of your winning is 0.2. So if you play that game 5 number of time, if you play the game 10 number of time, you are expected to win two number of times. Brahmanand, yes or no? If you play 10 times, the probability of your number of time you are expected to win is 2. Got it? So if you want at least one success, let's assume that you want at least one success, then how many times you should repeat? 5. 5 is if this 1 upon 0.2, 5 is 1 upon 0.2. So if P is a probability, you run the experiment 1 upon P number of time, you are going to expect that at least one solution you would be able to get. So the probability is 0.14. So 1 upon 0.14 number of times you should repeat this thing. Can you tell me that what is this value? If you randomly create a state something and run these many number of time, then you are going to expect that one success. Okay. So can you tell me that what is 0.14? 1 upon 7. So around 7 number of time. Okay. So one first chance, second chance, third chance, fourth, fifth and sixth and seven. So if you run 7 number of experiment, you are expecting that at least one time you would be win. So here you are going to spend 3 steps, 3 step, 3 step, 3 step, 3 step, and here you in the 4 step because you are going to win. At that time I am telling that you are going to spend 4 number of step. So to get the solution, these the fail attempts, how many? 6 multiplied by 3 plus 4. So this many number of steps you will be able to get the answer. I can modify the algorithm in this way. This is a speculation, right? Not the speculation. I'm telling about probability. So probability is not a speculation. Okay. So nobody can guarantee, but probability is expectation, and that is a science. Okay. You cannot tell that it is wrong. Okay. Most of the time it is going to happen. Make sense? Okay, so so if you want to increase it, try to find out a mathematical notation that say that if you do the 100 timing, what is the probability that you would not get a single success? Try to solve this particular problem. So try to see that how you find out that probability. So that probability is going to be very less. Okay, very less. If you try to see that, as I'm telling that out of the 7 chances, at least one you are expected to get one success, but if you are not concerned with the if you are not okay with that, try to find out the probability that if I perform this operation 100 number of time, then what is my probability that I would not be getting any success? So it is going to be very less. It's a homework for you. Please try to find out. Okay. So, this was the one thing. Another thing is this that as I told you that in the 86% of time you are going to be stuck. So what happens that you are actually into the board position where everywhere the values is going to be the same. So when you are stuck, what to do? So the idea is this that you are allowed to have the sideway moves means you randomly go to any because now everything is fine. All the places and all the other movement have the same value. So it says that you go into any one of them. Okay, this kind of move is called the sideway move. So it says that go to any one of them. How many sideway moves are there? Infinite because you can not infinite actually 8 to the power 8 any other configuration you can go and then you can continue with that. If you are stuck you can go to any other configuration and proceed. Okay. So so this is a very large number. So you cannot consider all of them. So so one another way is to do something like this that you put a limit on this. For example, only 100 moves I am going to do, because when you are going to do a sideway move, after that again you may be in the same scenario that everywhere the value is same. So again you would make a sideway move because all the values are same. So how many times you can do it? How many steps you can perform? You keep doing thing. Okay, so it is going to it take infinite amount of time and no progress you are going to make into the search. So another way says that we have seen earlier also into the DFS case that in all these scenarios what we generally say, we say that don't go beyond a particular limit. For example, don't go beyond the 100 number of steps. After 100 steps, don't explore anything. So what happens that you started doing sideway move. After 100 steps you say that no, looks like the solution is not going to be given. I would randomly start from someone else and then try to find out the problem. Randomly start, then try to find out the problem. If you change this algorithm in this particular way, now 90%, 94% of the cases you'd be able to solve the problem. Okay, however, number of steps are now increased, and on an average it is going to take 21 steps when you are actually able to solve the problem, and 64 steps when you are actually going to fail. Why 21? Why 64? So you know that now 100 now you started a board position, you are changing, and if you are stuck, then also then you are making the sideway moves, and after 100 steps what is going to happen? You, if you still don't get the solution, you are going to tell that if you still don't get the solution, then you are going to tell that I would come back and reinitialize the things and find out the solution. So failure cases are going to be 100 large. However, successful would be lesser than this. Okay, they would be in between. If you find out the success, no queen is attacking to each other, then you say that I'm done. So that's why the successful cases are 20 going to take on an average 21 number of steps. However, the failure cases are going to be of 64 on an average. There are a few more variation of the hill climbing, and one of them is stochastic hill climbing. Very interesting idea. Actually, it says that let's assume that what I say. Let's assume that you are here, okay, in this particular scenario, and the possibilities are these are the possibilities that from here you can go here, here, and here. Okay, let's assume the goodness of your place is again 10. The goodness of this is 5. Goodness of this is 9. Goodness of this is 11. Goodness of this is 15. Goodness of this is 12. Goodness of this is 5. This is 11, 13. So let's assume that these are the goodness of the place. Now I have a question. In which direction you would go? Hill climbing says in which direction you would go? In the direction of which value? In the direction of which value? Please type. Please type. Please type.
Maximum steepness.
Please type. Which is that direction? So you want to increase the value. So it is going to be 15. Okay. It is going to be 15. Okay. So in general hill climbing, you would go into this particular direction. But into the stochastic hill climbing, it says that okay, that is fine. It says that I am going to consider because 5 is a bad move, 9 is a bad move, 5 is a bad move. So these are the places, there are 4 places where I wanted to go. How good it is? 2. How good it is? 5. As compared to my current location. How good it is? 1. How good it is? 3. Okay, because here the value is 10. Okay, so the summation of overall goodness is 3 plus 1 plus 5 plus 2. How much it is? 11. Okay, total summation is this. So in this particular direction, it is 3 by 11. Probability that I would choose this particular direction is 3 by 11. Probability that I would choose this particular location is 1 by 11. The probability that I would go into this particular direction is 5 by 11. Probability that I would go into this particular direction is 2 by 11. Understand? So I am going to assign a probability, and based on that probability, now I am going to decide that in which direction I would go. Once again, if you can see that the highest value is with this only. So 5 by 11 is the highest probability. So most probably you are going to into this particular direction. But it may be possible that you don't go into this particular direction. Let me tell you how. So let's say in this particular setting, let me make 11 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So let me name also. This is the A location. This is B location. This is the C location. This is the D location. So I say that 3 places I am going to write A, and one place I write B, and 5 places I write C, and 2 places I write D. Once again, I have created a chit. And then I have, let's assume that I have created a box. In this box, I have cut all these chit uh, and I have put it like that. Okay, I had cut it and I had put these chits into here. C, D, and I have let me shake it well. Let me shake it well. Okay, and after that I close my eyes and take one chit out. Do you understand, everybody? Jyotirmani, Jyotirmay. I have created this way chit and I have taken the one chit out. What is the probability that I am going to get C? 5 by 11. What is the probability I get A? Is 3 by 11. What is the probability I get B? 1 upon 11. What is the probability that I get D? 2 by 11. Okay. But can you guarantee that I would go into this direction? No, anything is possible, na? Even this B probability of B is very less, but it is possible that I pick that particular one only. So the probability, this is how you apply the stochastic hill climbing, that you distribute with the things with the probability with their respective probability, and you go into this particular direction by setting up the probability. So in which direction you are going, you are not sure. Definitely you would be improving, but it may be possible that instead of this direction, you go into this particular direction. Sir, your screen is not visible. Is it problem at my end? Sanjeev, everybody, can you see the screen? So what I was telling that in this way I can assign the probability to each of the good directions, and then I can pick any one of them. Only the point that I wanted to make is this, that even if this is the best way, the probability of going to direction is very high, but I can go into the other direction also. Make sense? Next one is a first choice hill climbing. This is another way where I'm telling that I'm going to consider a kind of way in which I am going to consider all these things. Okay, so what I mean by this, that let's assume that I am here and these are the things in my nearby area. So I have decided that I go first consider this and go into this particular way in this particular order. Let's assume that I decided in this particular way. So let's assume here the value is 10, here is value is 5, here is value is 9, here value is 11, here is 15, here is 18, something like that. So I am actually the algorithm is self-explanatory that says that first I would see 5, I would reject it, 9, I would reject it, 11 is the improvement for me. I would go into this particular direction and keep doing again once from here itself. Okay. Yes or no? And another is the random restart hill climbing. And this is the same thing that we have few minutes back talked about, that whenever you are stuck, you are going to randomly restart your position and you again start doing the same thing. And we have few minutes back discussed that there is a probability associated that if the success probability is 86%, means if you perform this operation 0.14 number of time, 7 number of time, you are going to you are expected to have one success. So this is another way. Okay, it's the same way that if you perform the steps 1 upon p number of time whenever you are stuck, so you would be able to find out the solution. Another method, so it is completed. Okay, one thing that we have seen today is hill climbing. Another thing that I wanted to tell to you today is the simulated annealing. This is again a very interesting idea. Again, This is coming from some other domains such as metallurgy. People into metallurgy, na, they do something that they heat the material, and they, for example, if you want to make something, okay, you want to do the casting, you want to make a glass, okay, so they have some mold in which they put the things, and now their iron is very hot, and it is now it is into the liquid form. Then they fill it here and they start decreasing the temperature. So temperature was initially 1000, then it becomes 800, then 700, then after that when it become 100, then 50. So when the temperature is very less, then the things are actually settled, and it means what, that it has, we have actually done our process. So standard way of doing all these things into metallurgical domain. So in the same way here, computer scientists have actually tried to use and mimic their process to build some kind of solution. Again, the idea is very simple, and let me tell you what it is. So it says that along with the problem, once again, everybody please focus, that along with the problem, I'm also going to produce some kind of schedule. And what is schedule? So time schedule is something like this, that with respect to the time, there is some value. Okay, schedule is this particular table where 1, 2, 3, 4, 5, 6, say 1000. Okay, so the value would be 30, 50, 90, 10, 8, something, some values are there, and the last value is actually 0. So if the value is 0, then it means that your time has actually ended. Make sense or not? So this schedule is also provided to you where the some values are there. Along with that problem, some schedule is also provided, means how you are actually maintaining the temperature, something related to that. Here no physical significance of the temperature is there, but you assume that there are some values. So
Sir,
how
value
I'm going,
is in decreasing mode or increasing mode, sir? Temperature is increasing, so
yeah,
value is in decreasing mode when
okay,
we are expecting
interesting.
to reach zero.
Yeah. We can think that it is 130, then 120, then 10, something like this. However,
Yes, sir.
it is not required. Okay, it may be also possible that they are not into the direct order. Only important thing is this: when the value becomes 0, then I am going to stop. Okay, these values are into the order; they should be. But sometime it is not in order. It is also fine, because sometime now, if you wanted to make something, so if you are cooling something, then after that again heating for some time, then cooling, then heating, then cooling. So you are doing these operation in between. You can also do those kind of things. So if you want to make something very good, sometime it may be possible that multiple time heating is also required. I'm not sure about that, but point that I wanted to make is this, that they are some values. They should be into the order, but it may also be possible that they are into not in the order. I'm interested in 0 at the point when it is 0. Okay. Yes. Okay, so let us see this algorithm. Algorithm is very simple. It says that first you see the schedule, that what is your schedule, okay, and find out that what is the time. If time is equal to 0, then return the current state, whatever your current state is. So initially, what you do, that you take the problem and find out that what is the initial state. You say that I am into the your current state is the initial state. So you find out the into the problem formulation that what is your initial state, and you keep doing infinite number of time where t is actually this particular thing, and then by this t you are going to get something that is the value. Okay, this t is actually schedule. If you ask the schedule, schedule means these values are into the schedule. If this value is 0, means with respect to some time you get the schedule as 0, then return the current value, whatever is you have, you return it. Otherwise, a randomly selected successor of current. What does it mean? That you are here, these are your successors, these are your successors where you can go. You randomly pick any one of them. You randomly pick this one. So few minutes back we were talking about this was the value 10, this was 9, this was 5, this was 11, this was 14, this was 3. So you randomly selected someone. So let's assume that I picked this one. Delta E is equal to next that value minus current that value, means it wanted to see that what is the difference. So next one is the, for example, if you selected this one, this minus current value is negative because your value is 10. So this is a bad move. Okay. So you miss it. So you go here and find out this schedule again, sample something else. you don't do anything. If it is a bad place, you don't do anything. So next time, let's assume that you pick this one. Okay. So you pick this one. So there is a catch. Okay. Right now, whatever I told, take it with a pinch of salt. Okay. That you've considered this particular place. So if delta is greater than 0 means it is a better place. Two things could be possible. Na? Whether it is a better place 14 or you pick 9, that is a worse bad place. So if it is greater than 0 means if it is a better place, then you go to that particular place. But if it is a bad place, else condition means you are seeing 9, then current is equal to next with the probability e to the power delta e upon t. And this is an important thing. So if once again, please focus. You are here. These are the things you randomly pick one location. If this location is greater, has the higher energy. Energy is only the difference between these things. It is have the higher energy. Then you go into this particular direction. Definitely, you are going into this direction. But if it is this location, then you can go in this direction also with some probability. I'm not going to that much detail. It says that with some probability you are going to the bad direction also. This is what this algorithm says, that with some probability you are going to go into the bad direction also. And this is just a number because you have find out that there is some what is delta e? Delta e is a negative number. You know that. So therefore it becomes e to the power minus some value divided by t. T has come up from some here. So you are actually going to divide by this. This is some value. Okay. And this is actually the difference. So it is going to be a small, very small value. So the probability that you would be going into that particular direction is very low. So actually, let me see that whether this particular thing is there or not. So here, okay, here into this particular scenario, assume that you are here, you are at this particular place, you are at this particular place. Okay. So, or I can say that you are here. Let's assume that you are here. Okay. Let's assume that you are here. So two directions you can go, either you can go into this direction or you can go into this direction. So every time what was happening, that earlier what was happening, that you would go into this direction only, you would not go into this particular direction. This was the scenario. But now I am telling that you go into this particular direction, but with some probability you can also go into this particular direction. Is it a good idea? Yes or no? Is it a good idea? Yes or no? Is it a good idea? Yes or no? No, it is not a good idea. Why you are going to the wrong direction? It is not a good idea because somewhere, let's assume that you are here. There are two possibilities that you can go into this direction and you can go into this direction. So you are definitely going to follow this way because here, if you see that you are into here, you are going to direction. But this algorithm says that there is some probability that you can come into this direction also. Is it a good idea? No, because you are actually going into the wrong direction. But if you see the bigger picture, it may be possible that going into the wrong direction can take you out from this kind of, because if you reach here, you are stuck. You would not be able to make any other progress. But if you go into this particular direction, so maybe you would be able to reach this particular place. Okay. So it was not a good idea, but in the practical scenarios, it has found to be very effective. In many of the cases, it is found to be very effective. And going into the wrong direction is not promoted. It is only 1 upon e to the power minus v upon I. So it may be possible that you are stuck. So there is no much progress. So by randomly, you can fall down to other direction and then maybe from there you can pick up. Okay, next set of algorithm is very interesting, and this was the second thing that we have discussed. Now I am going to talk about a third thing. Okay, that is called the genetic algorithm. Genetic algorithm actually says that it actually depends upon the Darwinian theory that says that survival of the fittest. The fittest person survives. Okay, so by this people say that there was some when the Earth started, it was somehow sufficient fish started, and actually this is the real thing. Okay, let me tell you that what happens that when the earth is started, at that time it was a very it was hot. Okay, after that because of the reaction of hydrogen and oxygen, it becomes H2O, H2O, and a lot of H2A came, and it was then falling. After that, lot of water became, and in our then somehow people, nobody knows that somehow there some species started coming. When these species have eyes, so it was a big bang time. So different kind of species got started. So first species started into the water. The best one becomes fish. After that, something started like frog, which can be on the earth and both the places. Then monkey who can climb on the trees. Then chimpanzees, and after that human. So there are multiple theories. Sometimes people don't agree. Sometimes people agree. So we are not going into that particular thing. But looks like that if I cook up a story that it is going to be like this, the people are going to believe on that. Okay. I'm not sure about this, but let's assume that we believe into this particular way that there was something there was something survival of the fittest. We are going to see that whether is there a mathematical background for this, and we are going to see about that. Okay. So the idea is this, that the two things actually make new things. This is a very important thing. So in our 8 king current problem, you know that once again 8 king problem. So how many columns are there? 8 columns. So I can put some value, for example, 2, 3, 4, 8, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 1, 2, 3, 4. So let's assume that this is something, this number. What this number signifies, that you put in your 8 cross 8. Okay, I'm difficult for me to form, but let me try to make it. In 8 cross 8, you are going to keep second position. Okay, occupy the second position, then third position, then fourth position, then eighth position, then sixth position, then first position, then five position, five position. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7. So I have missed something, but you understand the idea that this number can be directly represented to a board position. Yes or no? Yes or no? Yes or no? If I give 8 numbers, you can directly make a 8 queuing instance. Okay, then I can say I can create another one. 8, 6, 7, 1, 2, 3, 8, 5. I can make another one. Okay, any problem in this? I can make something like that. Okay. Then why they should be unique? Should they be unique? No, no. I'm trying to make like this. They should not be unique. Okay, because who is stopping you to put all the things into 1 1 1 1 1 1 1 1 is also a right thing. Okay, they need not to be unique. Okay, they need not to be too unique. Now I am going to give you something. Please see this. If I say that, what does it mean? If I say that this, what the, if I say this, that it means, once again, I'm telling, if it's the smaller one, take these numbers. If it is smaller one, take these numbers. If it is up, take the things from here. Once again, please be with me. I had two configuration, and I have used these two configuration to make two new configuration. The first configuration says that I am going to take 237127115. 237127115. And the second configuration could be, can anybody type? Second configuration could be what? Let me give you the hint. 4, please type before me. 4, 6, 4, 8, 6, 3. You understand? Everybody understand this? So two configurations that we had, using those configuration, we have created two more configurations. Okay. So this is the way to generate something into the real life. Okay. So our life actually goes in this way, that we combine two things and by this we create more. So the same thing is applied over here. This was a board position. This was another board position. So I had taken this part here and this part from here and I has combined it and now it is a new board position. And if I combine this part and this part, again they can give you another board position. So from these two things, I have created these two things. Another two things I have created. I have just one. I can create two more things. Yes or no? Okay, the genetic algorithm says into this way that it says that things are something like something called chromosomes, and these were the chromosomes, and they apply operation called mutation and crossover, and by this they create new things. Okay, and we want something to be very good because my solution should be very good. Fitness. What is the fitness? How good this solution is? So I want to find out something that is very good. So in our 8 queens problem, which is more fit, which has the lesser number of pairs of queens attacking. So fitness is a function that gives you that how good this thing. So once again, let me give you the idea. So you actually create some board position, random board positions over here. Whether they are good, no, but they are randomly created, so they may be attacking to each other. Then what you do, you pick a pair of them, pair from them. How to pick pair? Question is this: how to pick pair? This is the question number one. But you pick the pair and you delete them. Instead of them, you create their offspring and put these offspring into this particular population. I said population. Once again, I have created random board positions that I can create, that I can always create. From this, I have picked few and this did this thing. So this is one thing. And second thing, whatever new generation that I have from with this population, I created another population. And and after that, I am going to disturb few of them. I'm going to pick some, and some of them I'm going to invert their bits. How to invert? These are the two things I'm going to do. So from this population, what I mean by this randomly created population, I reach to this particular population. Then I do the same operation here, I get something else. I do something, I get something else. I do something, same thing, I get something else. After that, somewhere, after doing somewhere, I would be getting a solution that actually I wanted. I would be getting something that I wanted. My God. Does it looks like something that I would be getting something? It does not give any intuitive idea, okay? But it is going to work. Why it is going to work, we are going to see. This is how the word works, okay? It's a very different kind of mechanism that says. Once again, let us go into this algorithm and try to understand that what this algorithm says. The algorithm is telling this, that you have a fitness function and this tells that how good this particular solution is, okay? You have, and this fitness function find out that how many pairs of them are attacking. Then there are two numbers P, R, and M. They would come very soon. So we would see that. So the first step is to generate P states at random. Means initially you generated the initial population. Yes or no? Everybody tell yes that you understood this. Randomly generate a population. Yes. Then on that population you are going to do three things: select, crossover, and mutation. Select. How to select? We are going to come very soon. How many of them you are going to are you picking every pair? No, no, no. Few portion you are going to pick. Rest let them be there. How many I'm going to select? So I say that P. items I am going to select. So 1 minus R into P, there is some portion, the 1 minus R into P. Forget about this. This is not very much important. So uh, few portions you are instead in the population, everybody is not participating. Okay, only few portion is going to participate. Okay, to make the new things. So remaining things are going to go as it is into the next population. So they are going to be there, and from them new things are going to be generated, and they are going to put it over here. Okay, so this is what the crossover is. So whatever you are selected, you are going to make the pair. So how many pairs are there? R multiplied by P minus 2, half number of pairs, and they both of them are going to create two things. So R multiplied by P items again, uh, you are going to they make, so population is not going to decrease. Then new population is created. After this new population, you are going to pick randomly pick a m portion of the things, small portion, and you are randomly actually hitting something, means you are changing something. So this was earlier like this, now it becomes something else. So you keep doing this until you find out, and then after doing this, you evaluate each of them that how good they are. If the maximum fitness is less than the fitness that is required, means 0 or whatever you want, at least this much fitness things should have. If you were not able to find out that particular value, you keep updating until after some time you get the good thing. Okay. The question remains that how to select the things. Okay. So one thing could be that anything that has what is the goodness of your solution, and divide by summation of goodness of all the other things. This could be used as a probability of selecting a particular item. Another method could be that, for example, out of all items, you find out that these items. Once, 1 minute, 1 minute, 1 minute. Another method could be that out of all available ones, randomly you pick two items, and with the probability P, you pick the good one, and with the probability 1 P, you pick the wrong one. Randomly pick two items. Definitely one of them would be having the higher value as compared to the another. So with the probability P, you are picking the higher value. With the probability 1 P, you are picking the bad value. Rank selection. So here, whatever items are there, you put them into higher into rank. First rank item, second rank item, third rank. Why rank? Why rank? How to find out the rank? Because every item has a fitness. So with the fitness, who is the highest fit item? You can put like this. Highest fit probability of selecting is 1, probability of selecting 2, probability of selecting 3, probability of selecting 4, 4, 5, 6. Oh, ये तो गड़बड़ हो जाएगा. So let's assume that there are 10 items. So probability of selecting this item is going to be 10. This is 9. This is 8. This is 7. This is 6. Something like this. No. Probability should be, if 10 items are there, what is the summation of all this number? It is n into n minus 1 by 2. So it is whatever number it is. 10 is 10 into 11 by 2. It is 55. So 10 upon 55. Once again, I have done the corrections. That probability of selecting the first item is this, second item is this way. You assign a probability of their selections. And using this probability, if you pick the item, then it is called the rank selection. Once again, arrange the item into their rank with respect to their rank, and find out the probability into this particular way. Okay, this is the highest probability item, then lesser probability item. This is the rank selection. Another could be elitist method. Here, whatever number of items were there, you are going to arrange them into the increasing order of their fitness, and you tell that these items I am going to take it into the next generation. Definitely going to take into the next generation, and for the remaining, I am going to perform these operations, that who is going to be better or not. This is how we select. And genetic operations, we have actually seen that crossover and how to do the crossover and mutation. So if these are the two things, and let's assume that if this is the filter, then you can apply this filter to find out two offspring. Single point, 2 point also be possible. So all these things are possible. Uniform crossover. So all these things are possible. You have seen that how to combine. So here you can see that it is this. Here you can see that this is the thing, and here it is telling you 1 0 1 0 1 0 1 1 something like that. So different kind of filters are going to be used, and now you can see that how they create the offscreen. Mutation is important, and this is again a big thing that we do, and it is also a very interesting thing. So some point you randomly picked, and at this position it was 0, it becomes now it becomes 1. So if it has been 0, then it must have become 1. This is called the mutation. So you can tell that, okay, very strange kind of thing, na? So you randomly started by some set. After that, it transformed to another set. After that, it transformed to another set. After transformed to another set. After this, how can you say that it is actually going to work? So I would not go into the complete mathematical detail, but the idea is this, that you try to find out that you show using some kind of thing called a schema, that if anything that has a higher fitness, so probability that it is going to be into the next generation is actually going to be the high. So the actually this is interesting thing. I don't want to come because this is coming from the ML, more from the ML class. If you are interested, I request you to please see my go to this particular website. With the more detail you can find out in my website called ktheory.in/ml. If you go into this particular website, go to the resources. So complete machine learning lectures are there. So here you see that where genetic algorithm, lecture number 18. Okay. So you there is a video also and PDF also. So complete with the complete information, the things are there. If you are interested, you can complete mathematical proof, you can go by find out into this particular location once again. So what I was telling, that the probability of anything, what is the expected number of things, item which has a high fitness, what is the probability that it is going to be, how many items would be there with respect to this particular string at the time t plus 1, says that how many of them were earlier, what is the average fitness of others, and what is the strength of these particular thing. So you know that anything that has a higher average fitness, so this number is going to be larger. Okay, if average fitness is this and somebody has a higher average fitness, so it is going to propagate. So it is going to get more power. Okay, now this is the general idea. I will not go into the much detail. If you are interested, you can see that particular lectures. Okay. So this is a general idea. And the basic line is this, that more fit schemas will tend to go in influence. Means what? Whatever thing is good, their population is going to increase by applying this kind of method. You can see. So that's why the humans are actually becoming better and better. That we can say. Okay. So any questions on that? Any questions on that? Yes or no?
So, sir, in this particular algorithm itself, what kind of question we can expect? Means because this is too much theoretical portion. So, if I have to get a question from here, this particular theorem, so what or we will be asking like, okay, just write this theorem
It
or
is
like some
not that. You
uh,
can see that lot of computation has came. So be ready with the computation. We have actually told here that here na this is
huh,
the computation, that how to create these things. And after that, I think here also we have talked about that what is the probability and how what is the probability, what is the fitness of selecting a particular item. You can see that all these things are coming as a number game
no, but yeah,
question.
that's what means. What would be the question? Means we'll be giving some numbers and then some
Yeah,
formula
what
I
is the
need to apply.
probability? Yeah, what is the probability of next item going to be selected?
Okay,
All
so
these
probably
things.
here I'll be given like what is the fitness at HI and then
Correct.
summation.
Correct.
Okay,
If this is the fitness function, so out of this, who is going to be the more fit? The questions could be like that. You evaluate the fitness function on them.
okay. So we
Uh,
won't be asked like okay, just write this algorithm. So all these steps that we have here, right? We will be having some
those
questions
can
on
also be
this.
asked. I cannot tell that theoretical thing cannot be asked. Theoretical
O-
thing can also be asked.
Okay,
So, but there is a huge scope of creating the these kind of questions also means numerical questions also.
okay, okay,
Okay.
okay. Yes, sir.
Now now we are going to see another very interesting idea that is called the continuous state space. So what happens now? Till now we were thinking that if you are into this particular state, you have 4 or 5 next choices, and you which side you want to go, you have to decide. This was we were discussing. Right now, let me tell that let's assume that you are into the continuous state space. Means all the things are possible. Means you can go here also, here also, here also, here also. In between also you can go here, here, here. In between also you can go here, here, here. So how many choices are there actually? Infinite choices. Okay. So infinite when there are infinite choices, then which direction you can go? So if you start evaluating all the things, you would be stuck because infinite things are there. You would not be able to compute all of them and find out that in which direction you should go. Does it make sense? In the continuous space, if the space is continuous, so multiple things are here. Okay, multiple things are here actually. And infinite many things are there. So you in which direction you should proceed, you would not be able to get. Earlier when the space was discrete, you can say that only 5 choices you have. Then you each of them you evaluated and find out that looks like that this position is better, so you go into this particular direction. But now if the space is continuous, you cannot do this thing. Okay, number of next step becomes infinite. So how to solve this particular problem? There is no way. Discretize the neighborhood. So the best way is to discretize the neighborhood. You say that I should not be very much concerned with whether I'm going to here or here. So you say that these many locations are the same. You discretize the space, and then by this you can reduce the number of spaces are there, and then you'd be able to solve this particular problem. Does it make sense? Does it make sense? Does it make sense? So any other methods which actually uses gradient to find out that what is the gradient to this particular direction. So most of the time we actually into the mathematics domain, we apply calculus to see that what is the gradient into that particular direction. And with respect to that gradient, we proceed with something. But again, into the computer science, actual things are there that you cannot in the computer everything is discretized. So continuous handling with a continuous thing becomes very difficult. Okay, so this is actually not possible. You have to apply some kind of discretization methods, and then only you would be able to solve the problem. So even if you want to find out that what is your del f with respect to a particular variable, you would not be able to find out this because space is not continuous. Values are not available. So local one assumption is this that locally the things are actually discrete, and then by this if you apply some kind of things approximations, you would be able to find out that what is the derivative. For example here, if you want to find out the derivative of this particular quantity with respect to, for example, del xi, so earlier you cannot apply, but let's assume that there is some summation term over there. So summation means all the terms you can write. Summation is nothing. This is nothing. Okay, because it says that terms are there with respect to the plus. So if you find out the derivative, so all other terms which does not involve xi become 0. Only this term survives. It has a power of 2, so you can see 2 multiplied by xi minus xc, something like that. So the same kind of idea you can utilize over here. You say that 2 multiplied by xi minus xc and the summation of all those terms which are actually surviving. By this you can find out the derivative and then you can go into the direction. So ultimate thing that I wanted to tell here is the discretization. Next thing that I wanted to discuss today is the non-deterministic actions. And what is non-deterministic actions? Deterministic and non-deterministic, you understand now? Deterministic means what? You want to do it, it is going to happen. But non-deterministic, you are not sure that whether it is going to happen or not. Okay. For example, let us see that our vacuum cleaner, you remember that we had something, a setting called vacuum cleaner, where there was two rooms and in room there was a vacuum cleaner. There were vacuum cleaner machine and okay, there was a machine that can clean the things. Am I right? So this machine could be into whatever rooms. Out of two rooms, it can be into one room. It can apply some of operations, sucking left and right. These three kind of operation it can perform. Is today's session or is it part of the midterm exam? Okay, Brahmanand, whatever we are touching here would be the part of your exam. Okay, so it is not my thing. Okay, it is the BITS policy that whatever is being covered into the one class before the exam should come into the come into the exam. So again, should to ho nahi sakta. So now what I'm talking about right now is that my vacuum cleaner is actually problematic. He has some problem. Okay, some erratic vacuum cleaner. So what is the error? It also cleans a neighboring room. So one error could be that whenever he is into this room and you are telling that clean the room, it may also go into here and clean. And second thing, and it is not like that every time it is we doing. Okay, error is not, if error is such that it is not like that. So it may be sometime that you say that clean here, it also go into this room and cleans. Not every time. Second kind of error could be deposit dirt. It may be possible that when it was cleaning, that instead of cleaning it is depositing dirt over here. It doing reverse. So here, if here is a dirt and you are cleaning, no problem because dirt was already there. But if it was a clean room and you have put the button for cleaning, but it has deposited dirt, so room become dirty. So let's assume that this kind of scenario we have. In this setting, how many states would be there? Same number of states, na? Same number of states, because both the rooms are dirty. One room is dirty, no room is dirty, and my vacuum cleaner is here or here. Only these things are there. So what happens? Let's assume that you are into this particular state, and you say that clean. So it may be possible that it cleans the dirt from here and you reach to this particular state. No, 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 no. You reach to this particular state. Yes or no? Yes or no? You are into this particular state. You say that clean. So this is gone. You are into this state. Yes or no? Yes. But as I told you, both rooms it can also clean. So it may be possible that you are into this state. Yes or no? So now in this kind of scenarios, states remain the same. But transaction would lead you to more than one state. And now this and this both are possibilities. So transaction from room number 1 with the suck is going to give you a set that contains 5 and 7. Okay. So the search tree that actually, because you wanted to reach into this particular state now, you start by this search tree would actually contain some R nodes and AND node. This is called the AND R search tree, where you are into this state. If you say right, so you would be into right position. ये तो ठीक है ना? This is fine. But if you say suck, it may be possible that you both the rooms are clean or only one room is clean. So this is like that. Any questions on that? From this state, you can reach, if you apply suck, you can reach here also and here also. You don't know that in which stage you are. So if you think that if you want to solve the problem, you have to find out the solution in all the cases which are here. So for
Sir,
this is
on top of the tree, there are two positions. So in first case, on the top of the tree. So one is the room with garbage and another one is empty. Am I right, sir? So the robot must be in one of the room. So when we say suck, so it will go to different room. So the probability of one room is not there because the robot is already present in one room. Or am I missing something, sir?
no, I think I am not able to understand you. Should I be on this page?
Yes, sir.
Okay. So what I was telling, what is the problem? Also cleans the neighborhood room. Okay.
Yeah.
But it is an error. So you cannot tell every time it is doing. If it is every time doing, then it is not a non-deterministic one. Okay. So error is this, that sometime it cleans the neighborhood room. So when you are into this place and you say suck, so you would be reaching to this particular state because it has sucked the error, sucked the dirt from here.
Right, sir.
But because of this error, it may be possible that the nearby room he has also cleaned, so you can also reach it to this particular place.
Right, sir.
Okay. So what is the confusion?
Now it's clear, sir.
It's clear. Acha, acha.
Yes.
Take care. So what I was telling here, that when you apply suck, so these are the two positions which are possible. So if you want to solve your problem and you want to take this particular path, solution should be in all the branches, all the places. Means let's assume that here 4-5 things are possible. For all of them, you need a solution. So let us find out. Can I find out the solution over here? Here again, you apply the suck. If you apply the suck, it may be possible that uh, this room is already clean, so you are here only and suck. You can read here also, because the problem was this, that you can deposit that. So I think it is a representative diagram only. If you go right, you would be, because right is correct. Okay, if you say right, you would be into this particular room. If you say suck, so it may be the room could be cleaned, or both the rooms are clean, something like that. So it is going to build something. The tree, now you can see that the tree has a lot more problem. Okay, so if you go into this particular direction, you have to find out where is the solution. But if you go into this particular direction, for all of them, you need to create the solution. So once again, this is called the AND node. This is called the R node. So AND or search tree means what? That here when you go into this direction, so one node you would be encountering. This is the R node. This is the AND node. This is the AND node. From this AND node, this is the R node. This is the AND node. AND node had more than one things. Okay. And I think right is not, sorry, I'm sorry, यहाँ पे नहीं है. This is not, this is also a, and this is also a R node. This is AND node, because when you apply suck, so AND node is written by this thing. These are the AND node. Okay. How to find out the solution? From here you apply suck, then from here you come here, then you go right, then you come suck, and then you go find out the solution. Okay, next thing that we wanted to tell you is another problematic statement that one thing that we have seen just now is what? That when it is a non-deterministic, you are doing something but happening something else. Sometime it may be possible that your system is not fully observable. You are into the partially observable states. What to do? What is partially observable state? So whatever you are going to see, essentially what do I mean? That whatever you are going to see is not going to give you guarantee that in which states you are. Okay, your percept are not going to give you the complete information. Okay.
The instructions we are giving to robot to suck it, but we are not giving the instruction which room. So the thing is this example like partial observation.
No.
Right, sir?
In the partial observation, you are not sure that in which room you are.
Right, sir.
Let's assume that you are not your GPS has a problem.
Right, sir.
Now earlier you were every time sure that in which room you are, but now you are not sure that in which room you are. Let's assume that in this particular setting itself, where you are allowed to go to right, left, suck. Okay, these operations you can apply what? Right, left, and suck. You can apply. But now
Yes.
let's assume that your sensor for finding GPS sensor is bad. You are not sure that in which room you are.
Right, sir.
So I give this solution. Just consider this solution. Right. So this is the room now. So I say that right. So if there are two conditions, na, either you are in your thing, your machine is here or machine is here. If your
Right.
machine is here, it remains into the same room. If machine
Correct.
is here, then it goes into this particular room. So
Right.
after applying this instruction, your belief is that you would be into the room A. Then you give the option as next instruction is suck. Let's assume right now the machine is correct. Okay, we are only focusing on the partial observation. So after giving this instruction, when you give suck, then this room is cleaned.
Right.
Room number A is cleaned. Then you give the instruction left. Now the machine would come into this particular room. You again
Right,
give
sir.
the suck. So this room is also clean. So this step of instructions guarantees that you would be
Hmm.
into the final state.
Right, sir.
So initially you could be into this state. So I think this diagram is not that much clear. So when you apply left, then when you apply the first instruction of left, you would be into any of the, you could be in any of these states. Both the room had dirt and you are here. One room had dirt, you are here. This room has dirt, you are here. And both rooms are clear, you are here. So all these states 1, 3, 5, and 7, they become one higher level state. Okay, you can treat them as a higher level state. Initially, initially you are into this particular state. You don't know that what is your position. All the 8 positions are possible. Initially, you don't know that. So one state is this that you can be into any of the state. But when you applied L left, then you would only be left with these many number of states. See the beauty of this thing, this representation. If you say right, it means that you would be only into these kind of states.
Right, sir.
You're not sure, but your state would be this only. Here, if you say suck, then you would be left with these kind of states. If you say here suck, you would be left with 2 states only. So this room is clear and the dirt could be here or next room could be clean. On this, if you apply right, you go into this particular room. This is the possible state. If you If you say suck, then you would be the room would be clean. And similarly, the another direction that you go into the right direction and suck and then feel left and then you can commit here. So these are the final states. So earlier sets, one state can be combined and you can say that this is the belief state in which you are. Are you able to understand the belief states?
Yes, yes, sir.
Okay. So this diagram, whether it makes sense that earlier you were not sure, so any state could be there. So there is one higher level state where all the states are there. Take left, only these states are possible. Take right, only these states are possible. Then these super states are actually called as belief states. I request all of you to by yourself make this thing. Okay. So it's a homework for you that create a belief states for this problem statements. If you so are you able to see this? If I say suck, so this room would be cleaned. If here it is this room is clean, so only these many number of states are going to reside. Then you can take the left and right, then left and right, all these things you can see that you can make by yourself. Okay. So now my question is, if it is a partial observation setting, if it is a partial observation setting, then what you should go, what you should do, you should construct, the answer is you should construct the belief states to proceed. How to create the belief state? Again, you have to do the manually in this particular way. Initially, we assume that you are into any particular state, but taking this, number of states are reduced and these are going to be the belief states. Okay. Another problem, unknown environment. You don't know about the environment. For example, in the unknown environment, the idea is this, that you take some action, observe the environment and compute the next step. That's it. So one step you can only take. Okay. For example, this is a setting where 3x3 tiles are there. Here is your robot that wanted to go to this goal state, but there are few, let's assume that there are few obstacles. So he can, from here he cannot go into this and this direction. From here also he cannot come here. He cannot cross this particular thing. He cannot go here. So what is the way to go? Here, 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 and here. In this way he would be able to reach. But he don't know. So he can go into any particular direction. He can go here also and here also. So, and after that, he sees that he can hit this particular wall, explores that no, I have given this instruction, but I'm not able to go that. Modify the table. You don't know this direction going is not possible. So really this direction going is not possible. So he come back here, sees, try to go here and here. Whatever exploration he is taking action, observing his moves, and based on this, it is actually going to build the table. And after that, he would be able to find out that what is the right way to go. Understand? So idea is take action, observe your output, and then compute the next one. Randomly, you can think that in this way I can but after some time he would be getting more information about the environment. Then he can contact his table and find out the better representations. Okay. So there is no algorithm that can avoid the dead ends in all the state space. So there will be some dead end. It may be possible that it reaches to this particular place and it takes huge time to find out that okay, this all these directions are bad, so I would go into this direction. So come here and by this you would be able to explore and go into this direction. There are actually special kind of scenarios and which are actually very interesting. People actually try to do that and that they want to find out the solution into the scenarios when they are not alone. Else is also there. He is attacking on him. Those scenarios could be of multiple flavors. One flavor could be, for example, into the game, two players are there. They can cooperate. Okay, they can help each other to solve some kind of problem, or they can be adversary. Okay, they are competing each other to find out to doing something. They can cooperate. For example, if it is a game of football, So they are helping each other to throw the ball into the right direction. Adversarial, they wanted to disturb each other so that the person can not get the goal or whatever advantage he is aiming for. So in this adversarial kind of setting, if you want to find out the solution, it becomes very tricky to find out the solution. Because if you are going to put n number of moves, the second party or the adversary is also going to put n such thing. So for example, when you are going to have a move, adversary is going to have his move. Then again you are going to have a move. Adversary is also going to have a move. So in every alternate step, he may be getting a chance to put something to make you bad. So a simple setting could be that I say that there is some value. This value you want to be maximized because you want more profit or anything that let's be positive direction only. So you want to make this particular value to be larger. So if you want to make it larger, adversary would try to drag you and he want to give you the minimum value. So you want to maximize and adversary is going to minimize. Okay. So this is a very nice concept that even I can tell that who is Max. Max is a person. Who is Max? You are Max. Your name is Max. Did you miss it? So person who is playing this game would be called Max. Okay. So I would call somebody as a Max. Who is Max? Is the person who is starting who wanted to win the match. The human. Human is Max. Who is Min? Min is also a name. Name given to whom? The computer who is playing with me, or my friend who is playing with me. He is Min. I am Max because I wanted to win. He wanted to defeat me. So into competitive environment, there are two players. One is Min and another is Max. So let us see a kind of game, and you know that chess is who what best we can do other than if you don't take it example. For example, the chess. Chess is the first and foremost good example that we can take. So if I want to find out these words that whether the game of chess is deterministic or not, yes or no? Deterministic, yes or no? Is it deterministic, yes or no? Yes, yes. Is there anyone who telling no? Deterministic means what? If you have a board position and you wanted to move this particular king from here to here, is it going from here to here, or it can also with some probability go to this particular place? If it can go to other place also, then it is not deterministic. In the deterministic setting, every time if you go from here to here, you would be going to that direction only. Is this chess environment is fully observable or partially observable? It is fully observable because all the places you at the same time you can see that where the things are not partially observable. You see everything in one go. It is turn taking, your turn, then your adversarial turn, then somebody else turn, something like that. Two player, it is a two-player game. It is a zero-sum game. What does it mean by this? So you know that two output could be there. Min can win or max can win. Okay. Or there is a draw. Okay. So if the should I write in this way that output could be uh, win output is with respect to max is win, lose and draw. If it is win, how much max is going to get? One point. How much min is going to get? 0 point. If it is lose, then min is going to get 1 point and max is going to get 0 point. If it is draw, half is given to max, half is given to min. So if you find out the total, it was all the cases, the total was going to be 1. Okay, so that's why it is called the zero sum. That's why it is called as zero sum game. Okay, because the same number I'm going to get in all the cases. Chess has a branching factor about 35. Means when you are into one board position, there are 35 on an average 35 possibilities that you can go ahead with that, and 50 moves it takes you to do to complete the game around. So if you go deep down 50, so 50 would be the moves done by your adversary min. So overall, how many moves you are going to have? 100. So in the space, how many board position you are going to explore? 35 to the power 100. Such a huge number. It is 10 to the power 154. However, the graph has a lesser number of node, around 10 to the power 40 number of nodes. But we know that from one board position you go to this board position, and some are going to repeating also. So number of board position is also 10 to the power 40. That is too much. Finding optimal move is infeasible. Optimal we cannot find. Best move very difficult to find out. But it needs an ability to decide how to proceed. You need some ability to decide that what should be your next move. Okay. So there are few things that need to be decided before we go. S0 is initial state, whether who is going to start the move, who is going to start, what are the actions that he can, legal action that he can take, what is the result. If you are into this state, you take this particular action, then where you go, whether this particular state is a final state or not, means win or lose or check. So what is the value of, what is the goodness of this thing? All these things you must have to decide. So you know that very difficult to find out the solution in this particular domain. We are going to see some ways to do that today. So essentially the space is very large. The biggest problem is this, that you cannot deploy any kind of searching mechanism over here because the space is very large. Just see a smaller example. You know that tic-tac-toe is a very popular game where you put zero and crosses and you play the game in this way. So if you start from the blank move, there are 9 moves that the min can make. Okay, so max can put something x into 9 places. Then it is a min who can now put. So initially 9 places. Initially there are 9 such choice options that he can pick any of them. Then 8 choices would be there for max. Then 7 choices for again for max, then min, then max, then min, and 6 places, then 5, 4, 3, 2, and 1. So it is a factorial 9 number of nodes are there. Different kinds of node would be possible. And you know that in this state, O has actually win. In this state, nobody has win. In this one has won, something like that. So too many nodes are there. Even this small game. So Max should find a strategy that how do I fight. Okay, it is not like that. He cannot decide that I am going to make this way and win, because the point he was put this and this, the adversary would put 0 over here. So a definite solution, if he decides that I'm going to go into this particular direction, is not going to work. Definitely he have to decide about some strategy. So how to define this strategy? So one method could be that let's consider that there is some tree, this tree. On this tree, what is the right move? What is the right move he have to decide? So let's assume that this is some scenario. where he is going to decide. In this scenario, he is here. He wanted to find out that I want to do something. So he had to consider one ply means his move and opponent's move, and this then based on that he have to decide. Let's assume that there is some oracle that tells you that what is going to happen after this thing, and somehow you decided some has given that what is the goodness of the play after this particular point, and here you are to decide that in which direction you should go. Let's assume that a1, a2, and a3, there are three choices that you have, whether you should go take this particular move or this particular move or this particular move. If you want to decide on that, its strategy could be that you see that what the minimum can give you over here. What is the minimum min is going to give you here. What do I mean by this? That let's assume that after proceeding this into, let's here min has a three choices, and in one choice there is three, you can get the advantage of 3. Another choice you can get the advantage of 12. Another choice you can get the advantage of 8. So this min, what would be the move of min? B1, B2 or B3? Can you tell me what would be the move of min? It's very interesting to see your answer. What would be the move of min? B1, B2 or B3? B2? B2? Tell me more. Anybody else? Two answers I have. Everybody please answer. Once again. B1. Sandeep is telling B1. Umesh is telling B2. So look, this is the min who is deciding that what should be the path. He don't want to give you advantage. He want to put you into the bad shape. So he would not give you B2, but otherwise then you would win. You would be getting 12 advantage of 12. So definitely he is going to give you B1 because he is your adversary. This is not your move. You are going to do the move over here. Adversary would come. He would take the chance over here. So adversary would give B1, B2 or B3. What he is going to do? Once again, now you understand. Please answer once again. He would be trying to push you into this direction so that you get only 3 profit. Okay. So I write it here 3. That maximum profit is 3. In the same way, in this tree, 2, 4, and 6 is there. So he would push you to this 2. So here 2 is possible. So here also 14, 5, and 2. So adversary would push you into this direction, min. So you would be able to get only 2 profit. So from higher level, if you want to maximize your profit, this side you would be getting 3, this side you will be getting 2, this side you will be getting 2. So the best is going to be into this particular direction, because then by this you would be getting the profit of 3. So this is called the min max. This is called the min max search strategy. Min max. Somebody is minimizing you and you are maximizing on their minimum. Yes. So the same thing is this, that you are maximizing on the minimum. So minimax value, we call it min max value. So for each node you have to find out what is the minimax value. So that's why this is the optimal choice. Yes. Okay, the same algorithm is given over there. How to go ahead with that? So Actually, how to find out this? Actually, here in this particular example, we have told that somehow you get this information. But you know that this information is not available. Finding out this information, you have to explore huge tree. So is there a way that you can utilize to not go into the trap? So the method is this, that once again, I wanted to give you the idea and then I would close this session. Idea is this, that when considering the value of min, you find out 3. 3 is the minimum one that you can get. Okay. When you get any other tree which has the value 12, okay, you need not to what I wanted to tell. Yeah. So then you consider 12, then you consider 8, you explode once again. From here, you want to find out that what should be the value here. So you find out that the value is 3, you find out value is 12. As I told you that this need lot of things to find out this value. From here you explode, the value is 3. From here you explode, the value is 12. From here you explode, the value is 8. After that, you understood that this value should be 3. So the maximum profit that he can get is 3. Now, when you were expanding, I'm going to tell you a very important thing. When you are going to expand this particular tree, you expanded and you find out that the value is 2. You expanded this tree, you expanded this tree, expanded this tree. When you expanded this tree and find out the value 2, now you are sure that whatever value are here, this is going to take this particular decision, at least this much decision, at least this much value. Okay, the value that is going to come out of this particular place, this particular tree, that is going to be at least 2. And now since from this tree you got something 3, so you need not to further explore, because you are definitely going to take this path. You are not going to take this particular path, because if you got something of the 2, so this particular tree is not never going to give anything better than 2. So you need not to explore these things. Are you able to understand this? You need not to explore these things, because whenever you saw this 2 from here, you need not to explore these 2 things. Ordering matters. For example, here when you came into this particular direction, you find 14. 14 is better than 3, so you expanded 5. 5 is better than 3, you expanded this. When you find out 2, then you are not going to expand anything if there had been anything here. So by this you can tell that I can reduce some of the places which need an exploration, and this is called the alpha beta pruning. So this is the basic idea. So we would stop at this particular point, and I would not take anything beyond this. So it's a very simple thing, but if it is left, that is fine. Okay. So that's all for today. Thank you very much for joining. So hope you understood the idea that that searching is not very simple kind of searching. Okay. In this particular, in these sessions, actually, we are going to see the different ways of finding out the solutions, different kind of scenarios. If you are stuck, how to find out the best solution. Thank you very much. Thank you for joining this session.